So, welcome to the Good Vibration Seminar Series. We're here today for the 10th seminar of the second year of the Good Vibes Seminar's existence. We're happy today to welcome Arthur Saux as the speaker of the day, and Arthur will be shortly introduced by Sébastien Devers. And I would like to announce the next seminar that will take place on April 13th, sorry. It will be given by Luisa Fernanda Rodriguez Diaz from Saux University, and it will be about an improved determination of convective granulation noise properties using 3D stellar atmosphere models. So welcome everyone, and Sébastien, if you want, the floor is yours.
Okay, so hi everyone. As Rita said, it's our pleasure today to introduce Arthur Saux. So he's a PhD student at Exeter University. And so just a few words about his background. So he did his undergrad studies at Sorbonne University in Paris. And then he joined the Master of Engineering at the École Centrale Lyon in France. In this place, he was introduced to stellar physics by Isabelle Baraf, who is now his supervisor, a PhD supervisor. So he did an internship with her. He also did an internship in planetology there, and they managed to convince him that it was much more fun to do astrophysics than engineering. So he then joined the masters in astronomy and astrophysics at the Paris Observatory. At this occasion, he did his master thesis at the CEA with Rafael Garcia and Lisa Bunier on stellar identification and classification. Since 2019, he's been doing his PhD at the University of Exeter with Isabelle Baraf. So he's working on understanding the physics of waves inside the stars using hydrodynamic simulations. He's interested in the internal gravity waves. He will talk about this in his presentation, I think, which we all know is important, in particular for the transport of angular momentum in stars. He's due to end his PhD in March 2023. So he will probably very soon be looking for postdoc positions, I think. Over his PhD, he also attended the Kavli summer program last year, where he worked on inversions of stellar structure with Sarbani Basu and Earl Ballinger. So he's currently co-author of 2 refereed papers, and he's first author of a recent paper. I think that's what he is going to talk to us about today. He mentions also papers in preparation with Sarbani Basu and Earl Ballinger and Rafael Garcia and Lisa Bunier. So as I said, he's going to finish his PhD in March 2023. And so having said that, I will leave you the floor, Arthur, for your presentation.
Thank you very much, Sébastien, for this introduction. So I will start by sharing my screen. Is it okay? Can you see my screen and the cursor here? Okay, perfect. So thank you, good morning, and thank you very much to the committee for offering me the opportunity to present my work in this seminar today. And thank you everyone for being present. So today I'm going to talk about modeling waves in stellar interior using hydrodynamical simulation. And in particular, I will present the impact of numerical techniques that consist in artificially enhancing the luminosity of a simulation. So in this presentation, I will show that how we can use multidimensional simulation to study wave physics, because even if observation of these waves have revolutionized the study of stellar interiors, their physical properties remain poorly constrained in the stellar context. So, as you know, stars oscillate because of waves that propagate through their interior. And in this project, we consider waves that are excited by turbulent convections. And the importance of these waves in stars is twofold. So first, they offer an incredible insight into the dynamics and the internal structure of stars through observation. And secondly, we know that these waves can also have impact on these dynamics and the internal structure of a star. So these waves are known to be involved in a lot of different physical processes related to rotation, mixing, or magnetism. So in this talk, I'm going to focus on the impact these waves can have on stellar properties. So in this project, we consider an ideal case with where we neglect rotation and magnetism. So in this setup, you have two types of waves that are the acoustic waves that can propagate through the entire star, both in the convective zone and radiative zone. So these waves are relatively high frequencies. And on the other hand, you have internal gravity waves that can only propagate in stably stratified media. So this means this is in the radiative zone of stars, so in the internal core of low mass star and the radiative envelope of higher mass star. These waves are much lower frequencies than acoustic waves. And both of these waves are excited by turbulent convection through two main mechanisms that are Reynolds stress and convective penetration. So today, let's focus on internal gravity waves. So the first question we can ask is why we should care about these waves and why are they important in stars. So since they have been discovered at the end of the 19th century, internal gravity waves have been very intensively studied by the geophysics community because they are very common in the Earth's atmosphere and in the oceans. As you can see here on the right, two pictures of the excitation of internal waves here by these rising plumes of smoke. So these pictures are of the same phenomenon from below and from above. This picture was taken a couple of months ago during the eruption of the volcano in La Palma. And you can really see here a rising plume that is exciting waves in the center here and internal gravity waves that propagate outward radially here in the concentric circles. Also, in order to better understand the property of these waves, they have been very widely studied in an experimental context because in this way you can easily explore the parameter space of simplified models. So today we know that these waves are really important because they can transport angular momentum, energy, and chemical elements, but also they can carry information about the medium they are propagating through. So their importance in stars is important, sorry, because they are known to take a part in a lot of different phenomena. So concerning their transport properties, they have been proposed to as possible solution for a lot of different phenomena, such as the uniform rotation of the solar core or the differential rotation of the sun. They could be possibly involved in the solar neutrino flux, or they are involved in a lot in the mixing in stars. And concerning their the transport of information, they are known to be able to give information about the measurement of stellar rotation, the detection of magnetic fields, but also to probe core overshooting on internal mixings in stars. And they can also give us information about the mass and age of massive stars. So, as you can see, these internal gravity waves are really important in stellar physics. However, the main issue is that lots of their actual properties in stars, such as their generation spectrum, for example, remain unknown and are difficult to constrain. This is mainly because internal gravity waves are 3D, nonlinear, and anisotropic phenomenon. So developing an accurate analytical model is very difficult. and consequently, their observation remains very challenging. This is why we need multidimensional simulation in order to test the analytical models and also to guide observation. This is essential for past and present missions, such as Kepler or Plato, but also for future ones, such as Plato. So the question here is how we can use multidimensional simulations in order to constrain internal gravity waves properties. So this is what I'm going to talk in the next sections, how we can use numerical simulation as alternative laboratory to test waves physics. So when you run the simulations, what you do basically is that you solve your hydrodynamical simulations, so conservation of mass, conservation of energy, and conservation of momentum. Plus you solve an equation for transport of energy and your equation of state. You can also possibly add the rotation of magnetism, and this is something we are working on in our group here in Exeter. But the main problem is that multidimensional simulation of stellar interior is a real challenge. And in the next slide, I will explain why it is so complex. So first, you have a very wide range of timescales. So you have the nuclear timescales that is of the order of a couple of gigayears. Your thermal timescales is 10 million years, but you go down for dynamical process such as wave down to a couple of minutes, or for convection to a couple of days. So now there is also a very wide range of length scale. You have the radius of your stars that is quite huge, of the order of 10 to the 8 for the sun, for example. And if you're studying waves, you have a very wide range going from 10 to the 2 to 10 to the 8 meters. And in simulation, you can go down to the photon mean free path that's in the order of the centimeter. But if you look also at one given quantity, so here on this plot on the right is the density as a function of radius. You can see that near the center of the star, the density is of the order of 10 to the 2 gram per cube centimeter, but is going down to 10 to the minus 6 gram per cube centimeter near the stellar surface. So this means you have 8 order of magnitude difference for the density between the center and the surface. The third difficulty you have to face is that the flows in stellar interiors are in a very complex regime of parameters. So your Reynolds numbers, that is going to quantify the ratio of your inertial effects to viscous effect, is very huge in star. It is much larger than 10 to the 6, and it can go up to 10 to the 12. So this means you have very turbulent convections in star, and the viscous effects are very small. Your Prandtl numbers that is going to quantify the ratio of your viscous to thermal effects is also very small, much lower than 1. And your Mach number can range from 10 to the minus 10 to 1, depending on where you are in your star. So this is for the challenges you have to face in the physical context, but you have also numerical challenges that are related to the computational time, because you want to have your results of your simulation in a reasonable amount of time, not to run your simulation for years. You have also to face difficulties related to time and spatial resolution, and also to face numerical stability. So in order to face all these challenges, you have to make approximation. So first, you can make approximation when you solve your equation. You can choose to solve the equation in a fully compressible medium, or for example, to make the inelastic approximation. You can make approximation for your spatial geometry. So are you going to model the entire star or only a tiny portion of it. I'm going to use Cartesian or spherical geometry. And finally, you can also make some physical simplification. So you can, if you do a lot of physical simplification, you have a more ideal system. But if you choose to make as few simplifying assumptions as possible, and thus try to model a more kind of realistic system, one of the main issues you have to face is the problem of thermal relaxation. This thermal relaxation timescale, so you have to run for one thermal relaxation timescale your simulation in order to be in a thermal relaxed state. And this thermal relaxation timescale is extremely long. So it is given by this expression here. And just as an indication, in the Sun, it is approximately 20 million years, and it is impossible to run a simulation for that long. So to face this, two approaches have been developed. So first, it is to assume that you have to assume a dynamical steady state. So this means you wait your simulation to have a total kinetic energy in your system that is approximately constant. And the second approach is to artificially enhance the luminosity of your model. So this is a technique that has been commonly used by the community. And as you can see here in this expression of the thermal relaxation timescale, it is inversely proportional to the luminosity. So this means if you increase luminosity, you're going to reduce this timescale. And it is very common to boost a model, so to artificially increase luminosity by a factor of 10 to the 4 or 10 to the 5. So you can see this will decrease by a lot your thermal relaxation time. So now just a bit more detail about how we boost a model. So when you boost a model, you artificially increase the luminosity of the star, and you accordingly increase the thermal conductivity of your star. So this means you're going to inject more energy in your model, and you're going to transport it faster. So this is supposed to accelerate the evolution of your simulation, of your model. So you have to increase these both quantities in order to keep your relative temperature gradient identical in each model. So then your boosted model is going to stay as close as possible as your reference model. But the thing is that it has been suspected that this technique can impact your stellar properties, physical properties, and particularly the physics of internal gravity waves. So the main question we want to answer here is, can we use these artificially boosted models to make predictions for more realistic system? And if you want, we have also performed study about the impact this technique can have on convective penetration, or how we can use the simulation to try to help answering the solar modeling problem. So if you want more information, you can look at these two papers by Paris et al. 2021 and 2022. But here in the following, I will show that we can use internal gravity waves. We can study internal gravity waves physics with a boosted simulation, but we have to be very careful on how we do that. So for this project, we use the music code, that is a numerical time implicit code that solves the hydrodynamical equation in a fully compressible medium. So this means with the simulation, we can have both internal gravity waves and acoustic waves. And here we are working in a 2D spherical geometry with radius and collatitudinal and collatitude. So our reference model is a solar-like model based on a 1D model, and our radial range is from 0.4 to 0.9 of the stellar radius, and the collatitudinal range is from 0 to pi, so we are modeling a hemisphere. So on the right here, you have the plots showing the Braun-Weishaler frequency as a function of radius. So the region we are modeling is a region here between the two hashed region, with here the relative zone and here the convective zone. So this quantity is important because the Brun-Weisser frequency is the maximal frequency that can have an internal gravity wave. So in order to compare boosted models with a non-boosted model, we use 4 simulations. So we have a reference simulation with a luminosity, a reference luminosity L star that is very close to the luminosity of the sun. And we have 3 boosted models. So we have boost 1D1 that has luminosity that is boosted by a factor of 10, boost 1D2 by a factor of 100, and boost 1D4 by a factor of 10 to the 4. In this third column here, you have the convective turnover timescales that is defined by this expression here on the bottom right. And this gives you an idea of the characteristic timescales of your convective processes. And as you can see, it decreases when you boost a model. So this is something we can expect because, as you can see here, this token is inversely proportional to the RMS velocity. And when you inject more energy, so when you increase the luminosity of your model, you can expect your convective motions to be faster. This last column here is the number of tokens we have been running the simulation for. So here in this slide is presented 4 snapshots of the simulation, 1 snapshot for each simulations. So here you have the reference simulation, and here are the 3 boosted ones. So this snapshot presents the radial velocity in our models, with here the radiative interior, where you can see concentric circles or spirals that are characteristic of internal gravity waves wavefront. And these wavefronts present an inclination with respect to the convective boundary, and this inclination is an indication of the frequency of your waves. This comes from the dispersion relation for internal gravity waves that is given here, where you have here the ratio of the frequency of the waves to the Brun-Weisser frequencies, that is equal to the ratio of the horizontal wave number to the total wave number. This allows you to define an angle between the horizontal wave number and the total wave number. That is basically the angle between the convective boundary and the perpendicular to your wavefront. So then you can see that if you have more inclined wavefronts, this is an indication that you have higher frequency waves that dominates in your radiative interior. What's interesting to see here is that if you look at this boost 1D1 model and boost 1D2, you have more inclined wavefronts compared to the reference model, indicating that you have higher frequency waves dominating when you boost a model. On the other hand, here you can see that the radiative zones of our most boosted models, boost 1D4, already present different structure. You can see here really the internal gravity wave wavefronts. So this is the first indication that boosting a model can impact the structure of your radiative zone. Then you can see that here in the convective envelope, we have very similar structure in the 4 models with characteristic upflows in red and downflows in blue. They are very similar in the 4 simulation. So this is something we can indeed expect, because in a convective zone, you have, as we have seen, a characteristic time scale, tokens, that allows you to define a convective frequency that is just 1 over tokens. But you also have a scaling of the velocity there. You know that the RMS velocity in the convective zone scales at the luminosity to the power 1/3. This is a result we find with our simulations. Here on this plot, we have the RMS velocity normalized by the luminosity to the power 1/3 as a function of radius. And here we have the convective boundary. And you can see that when you normalize your velocity by the luminosity to the power 1/3, you can indeed obtain very similar amplitudes of the velocity in the convective zone. However, this relation does not hold in the radiative zones on the left. But you can see that the amplitude of your waves increase with increasing luminosity. So, given that internal gravity waves results from the dynamical interaction between the convective and the radiative zones, the radial kinetic energy in both regions are useful diagnostics to analyze properties of internal gravity waves. And since waves are periodic phenomenon in space and time, our analysis is performed in the spectral domain, both spatially and temporally. So to compute this spectra, we used a temporal Fourier transform of the radial velocity, and then we perform a decomposition of the spherical harmonics basis. And this will give us the spectrum of the radial velocity that scales at the squared amplitude of the radial velocity. So first, let's have a look at this spectra, this spectra in the convective zone. So on this slide, you can see 4 spectra, one for each simulation. Here, spectra of the radial velocity as a function of frequency in microhertz here, and as a function of the spherical harmonic angular degree L, ranging from 0 to 200, with here the large scales and here the small scales. The color bar represents the spectrum of the radial velocity, so normalized by the luminosity to the power 2/3. And we computed this spectra in the bulk of the radiative zone at 0.762 of the total stellar radius. So how we have just seen an important quantity when you study convection zone is the convective frequency that is given here in this tab on the left, and as expected, its value increases with the luminosity. So here we have then normalized the frequencies by this convective frequency for each model. And as you can see, what's interesting here is that you have very similar spectra for the 4 simulation when you use these 2 scaling relations. You have here a lot of energy in this region, in the 4 spectra. So this is approximately between L equals 0 and 100 and between 0 and 5 omega conv. And this is an important result because it means that using appropriate scaling relation, you can obtain similar power spectrum independently of your boosting factor. But something to keep in mind here is just that even if you have that 5 omega conv, so your frequency range in microhertz will be different in the 4 simulation. Because here 5 omega conv in the reference model correspond to approximately 6 or 7 microhertz, but in the most boosted models, 5 omega conv correspond to 160 microhertz. So now if we look at the same kind of power spectrum, but in the middle of the radiative zone, so here at 0.494 of the stellar radius, this is at such a depth, so it's sufficiently far away from the convective boundary where we can assume that waves are the main contributor to the radial velocity, and that we are not polluted by convective plumes that dive in the radiative zone. So here on this spectra, you have different color bar because there is no scaling relation for the radial velocity in the radiative zones. But the important thing to notice here is that you have a common pattern of bright ridges here in these four plots. And these bright ridges present a discrete nature that are characteristic of internal gravity waves, as we will see in a minute. The important message here is that this figure clearly shows that when you increase luminosity, you have more energy in higher frequencies and in lower scales. So as you can see here, you have a lot of energy at very low frequency and across all angular degree L. And when you boost a model, this energy the dominant energy is shifted toward higher frequencies, and you have less energy at small scales here. Okay, so this is something you can expect from theory, because theory predicts that you have energy in your waves that follows, so in the excitation of your waves that follows the convective frequency. So in summary, here you have a redistribution of the dominant energy towards higher frequencies and larger scales when you increase the luminosity of your model. So in this slide, we compare our results with the previous results. So here we have our power spectrum for reference models that present very similar patterns as the one is obtained by linear theory here with the plot from Christensen-Dalsgaard 2014. And here we have a similar pattern also with the power spectrum computed in the relative zone of 3D solar-like models from Alban et al. 2014. So now, in order to confirm that what we see on this power spectrum, the bright dots of energy here are indeed G modes, we'll take a slab here of this power spectrum for L equal 5. So here is the slide of my power spectrum, but here it is plotted as a function of period instead of frequencies. This is because G modes are equally spaced in periods, and this is a property we can retrieve in music, where you can see here the peaks of our 4 spectra corresponding to the spectra for 4 simulations that are equally spaced in period. So now to compare with analytical prediction, we have used the oscillation code gyre, and we compare the computed G-mode frequencies, so here the vertical dashed lines, to the peaks present in our 4 simulation spectra. And you can see that indeed you have a very good match with the gyre prediction, but also it seems that your frequency are not impacted by the increased luminosity. So now that I have showed that we are able to model realistic internal gravity wave with music, I'm going to compare our results with some theoretical prediction. So one important quantity you want to determine when you study internal gravity waves is a radial wave flux. You want to know how much energy and where you're going to transport energy radially. So this wave flux depends on the excitation mechanism. And we have seen there is 2 main excitation mechanisms for the internal waves that are Reynolds stress and Plum's excitation, so convective penetration excitation. And there have been lots of models that have been developed since the 60s for these two excitation mechanism. But the problem is that this model leads to different prediction for the wave flux. So here in this study, we consider 2 of the most recent models that are the Le Cohanet Quartet 2013 model for the Reynolds stress and the Passon et al. 2016 model for the Plum's excitation. So in all of these models, what they do is that they take the momentum equation and they perturb and linearize it, and then they obtain a nonlinear source term here that is basically the divergence of the cross product of the velocity with itself, and then they use different models for the velocity. So in the Reynolds stress excitation, they model the velocity here with the Kolmogorov-like spectrum, and for the plumes, they define a model for the plume velocity that depend that is a Gaussian in spatial and time, in space and time. So in the Le Cohanet Quartet model, they obtain different expression for the wave flux that depends on the temperature gradient profile at the convective boundary. So here the first case is if you have a discontinuous profile, and here we only keep the dependence in horizontal wave number and frequency for the wave flux, and they consider 2 smoother cases, one linear and one tangent hyperbolic. Here, you can see that the dependence in horizontal wave number and frequencies change with this change in the temperature gradient profile. And D here is the size of your transition region where this temperature gradient profile is evolving. Okay, but here you have the waveflux that depends in power laws on wave number and frequency. In the Plum model of Paris-PSL 2016, they have defined, they found that the wave flux depends in a Gaussian way of the frequency here, and with new P here, that is a characteristic frequency associated with the Plum lifetime in the relative zone. And finally, in music, we estimate our wave flux using the power spectra of the radial velocity here. And here you have TS, that is the total integration time, Brun-Weisser frequency, frequency of your wave, and the radius. So here we plot our radial wave flux. In purple is the one we have estimated from music simulation. So it is plotted for an angular degree L equal 10, and at a radius that is R minus L max. So this means it is at a distance L max from the convective boundary, with L max is the maximal depth reached by convective plumes. So we can see here in purple that our wave flux peak around this vertical gray line that correspond to the convective frequency. So this is a result predicted by a theoretical model. And if you are next to this convective frequency, we can see that our power spectrum is broadly consistent with these two dashed curves that correspond to two cases of the Plum model with different frequencies associated with the plums. If you go to higher frequencies, we can see that our wave flux is approximately follow power laws that are broadly consistent with the Reynolds stress excitation models. However, it is very difficult to really disentangle the two mechanisms, but also to measure precise slope in our models because of the strong G modes we can see here in the wave flux. But in summary, here you can see that both Reynolds stress and convective penetration seems to play a role in the internal gravity wave generation. Okay, so now one last thing I'm going to talk about is damping of internal gravity waves as they propagate in the relative zone. So internal gravity waves can transport angular momentum through three processes that are radiative damping, the encounter of critical layers, and nonlinear wave breaking. So in this study, we're only considering radiative damping. So from the study from Press 1981, we know that the wave amplitude scales at the density to the power -1/2. You have a geometric term, and here this exponential is the radiative damping of your waves, with the function tau here that is defined by this expression, with L the angular degree, Carad is your thermal diffusivity, and the ratio of N Brun-Weisser frequency to frequency of the waves. So in order to compare the power spectrum we have in music to theory, we build a synthetic spectra. So we take the value of our power spectrum at a given radius, and then we multiply it by this exponential relative damping term. This is what we obtain here for an angular degree L equal 5. So you have here the power spectrum as a function of radius here in the relative zone and frequency here. And on the left, you have the actual music spectra, so computed at each radii. And here you have the synthetic spectra. You can see that we have very similar shapes here. This shape is characteristic of the damping of the waves. So it seems that we are indeed observing relative damping in our simulation. So this is something you also observe in a boosted simulation, but to do that, you have also to increase your thermal diffusivity by the same amount as the luminosity. This is essential in order to retrieve this theoretical prediction. This is because, as you can see here, you have the thermal diffusivity that plays an important role in your relative damping. If you want to retrieve the right amount of damping, you have to increase it by the same amount as the luminosity. Okay, but just keep in mind that even if we still retrieve the theoretical prediction when you boost a model. The boosting factor have an important impact on the spectrum of surviving G modes because you have more energy in high frequency waves and the damping will be increased. So in conclusion, the question we will try to answer here is, can we use boosting models to study internal gravity waves and make prediction for more realistic system? So yes, you can, because we have a scaling of the energy in the excitation region. The theoretical prediction for both dampings and wave flux seems to remain valid when you increase the luminosity, and the frequencies of your G modes are not affected. But you have to be careful because more boosting is equal to more energy in high frequency waves. And as we have seen, the characteristic frequency of excitation of your waves will be shifted towards higher frequencies. And the more you boost the model, the more this excitation frequency will be close to the Brown-Weisser frequency. That is the maximum frequency for internal gravity waves. And you have an important, also it is also important to increase relative diffusivity by the same amount as the luminosity, particularly when you study rotation. And you have to be careful if you boost your model by two important boosting factors, your model can evolve very fast and can lead to unrealistic or unphysical results. Thank you for your attention, and I'll be happy to take any question.
Okay, thank you very much, Arthur, for a very interesting presentation. So it's now time to take questions. So if you have a question, can you please raise your hand? As always, we encourage young researchers to ask questions. I don't see any raised hands so far. So I will perhaps start. I had perhaps a naive question. You mentioned that you need to increase the luminosity in order to be able to treat this problem numerically. But you also show models with not enhanced luminosity where you can actually see waves. So if you can produce such numerical simulations with no enhanced luminosity, why not do this all the time?
The main problem with that is for most of models, like it is very difficult to have a realistic state of convection, stable state of convection in a model if you don't boost your model. Like in a lot of models with different codes, like convection dies quite rapidly before you have a kind of steady state in your model before being able to analyze it. Does that make sense?
So that's what you have in your reference, the reference model that you show.
So no, in our reference model, we managed to run a simulation for solar-like models with a reference like a luminosity very close to the solar luminosity, but that is quite difficult to obtain for example, for lower mass star and with some other codes like that are not able to produce a realistic convection with the solar luminosity. They have to increase luminosity by 10 or 100 times. So this is the first study that shows the impact of increasing the luminosity of a model, but this is also one of the first times that a fully compressible medium and time implicit code like this is able to run a simulation, solar-like simulation with solar luminosity.
Okay, thank you. So I have Saskia.
Good morning. Thank you very much for this interesting talk. And I think following from Sebastian's question, you did, as I understand, this not only for a solar model, but I guess you want to extend this to models with different masses and radii potentially. And could you then at some point kind of give an advice or a optimal enhancement of the luminosity for which you still retrieve the physical properties, but you reduce the time that you have to run the simulation for so that it's balanced out what you want. Is this something you're working towards too, or can you do that already? Can you comment on that?
Yeah, so for now we are also working on 5 solar master to compare these results with start with convective cores, and particularly with this will help us to study the non-linearity of waves in the radiative envelope. But here with the 4 simulation we have, like we have seen that you can increase luminosity of your model to study wave physics, but you have to be careful on how you interpret the results, because, for example, the spectra of waves you're going to obtain, you can't really compare that directly with observation, because if you increase, as we have the convective frequency, or energy will be shifted toward higher frequencies. So it's still difficult to make a realistic prediction to compare with observations, I guess.
Okay, thank you.
We have Daniel asking next question.
Okay, can you hear me?
Yes.
Yes.
So thank you for the very interesting presentation. I also had a question concerning the boost factor. I was wondering if you could have a high value of the boost factor at the beginning and then slowly decrease it as you get to the end of your transitory state once you reach a steady state.
Actually, I don't have a real answer to that. This is something we have thought about, trying to do like an accelerate relaxation process and then kind of deboost your model to have a reference luminosity. I think this is something that's worth looking into it, but I don't have an actual answer for that for now.
Okay, Dominic, you had the next question.
Morning, Arthur. Thank you for the talk. I really enjoyed reading your paper as well, so thank you for that. So I have a question on the wave spectrum. So you're plotting radial velocity. I would encourage you to look at other things, because the G modes have their horizontal motion being dominant. And sometimes you can see some nuances, especially in the ratio of those, that can tell you that how the wave spectrum changes as a function of this boosting factor. I want to pick up on the point that you caught my attention on, which is the 5 solar mass star. Can you perhaps elaborate a little bit on what evolutionary stage and other physics that's going into that particular model that we hope to see in the literature soon?
Yeah, so we are doing same kind of comparison with 5 solar master at the ZAMS with 4 different boosting factors, with 1 reference model and the same boosting factor as in this study. And the objective here is to study internal gravity waves propagating in the envelope. So we are modeling from 0.02 of the stellar radius to 0.97. And the objective here is to study, because in this setup, as you know, like the amplitude of the waves will increase with as they propagate towards the surface. And we want to study the non-linearities that will appear, and to see if boosting a simulation impacts the non-linearities of the waves as they propagate towards the surface.
So I presume you're familiar with the paper from Ratish, the ex-PhD. Yeah, okay, good. Because I think the comparison of music with their code is going to be very valuable. So I look forward to that.
Yeah, that would be very interesting.
Okay, I see no raised hands. Perhaps I can ask another question. You mentioned at the very beginning of your talk that you were considering including rotation and magnetic fields. Is it something that you consider doing, or you're already doing? Because seeing how the magnetic fields interact with the G waves would be very interesting.
Yeah. So for the rotation, we have been running for the past year 3D models that includes rotation. So I'm also starting to study waves in these models. And for magnetic fields, this is still work in progress with music. So it's not going to be in a short time scale, but that's for a longer for later, but that's something we are also actively working on at the moment.
Okay, thank you. Jorn, you have a question?
Well, I wasn't sure I was young enough, but maybe I can try. Thank you very much for this very interesting, very valuable exercise. 2 points, 2 questions really. One, could you show again the slide of the frequency comparison at L equals to 5?
This one?
Yep. You're right that at least for the 3 lower cases, the match is pretty good, but for the 10 to the 4 case, it looks a bit more random. So do you have any comments on that?
Yes, so here particularly, I guess you are talking about. So
yeah.
This is not really clear to us, because here you have we have a less resolution for the more boosted models, because we have run it for less time. Because like we have to have a much shorter time step in our simulation in order to capture the physics of the convection. So these peaks are quite broad, so it's difficult to really compare at low frequencies here. But it also can be, as I said in the conclusion, that when you boost by a lot your simulation, you can have some modification of your stellar interior property. And this is something we discuss a bit in the BARAF 2021 papers that focus more on convective penetration, when you can see an impact of the boosting on the thermal background of your model. So
yeah, well, and of course there could also be nonlinear effects of the waves, which is to some extent the same thing. Actually, just a brief question about the use of the fully compressible code. Does that mean that your time step has to be short enough to capture the acoustic waves, or are they somehow dealt with?
No, yeah, we haven't really looked into it for now, but we are able to see acoustic waves. So here they are very low amplitudes here, but you can see above the Brun-Weisseler frequency here some bright dots here that are characteristic of acoustic waves. And this is something we want to look into it also in the near future, to try to see how we can study acoustic waves with a music code.
And then finally, of course, the elephant in the room.
Yeah.
What about 3D?
So yes, we are running 3D simulations too, but that takes a lot of time. We have no solar-like model similar to this reference model in 3D. That we are starting to analyze now. That includes also rotation. So results should be coming in the next month, I hope.
And qualitatively, do they look similar to the 2D results?
Yeah, we haven't.
An unfair question.
Yeah, it looks similar. Apparently, there will be a previous study with other codes that seems to retrieve similar properties for waves in 2D and 3D. And that's also why we run similar models, model as this one, then we are able to compare really 2D and 3D. Use this also impact internal wave properties.
Yeah, okay, well, thank you very much.
Thank you.
Okay, I see no more raised hands, so perhaps we can stop there. And Rita, if you want to say a few more words.
No, well, thank you very much, Arthur, for a very interesting talk about very difficult work. Thank you everyone for being here with us today, and I guess that we'll see each other in a month from now for Louisa's talk. Very soon. Okay, thank you everyone, and thank you, Arthur, and see you next time.
Bye-bye.
Thanks. Bye-bye.
Bye.
Thank you.